Hello everyone. In this third video, I will introduce you to the concept of radio observations of meteors. So in the first two videos, I explained that when a tiny particle called a meteoroid enters the Earth's atmosphere, it heats up, burns, and is vaporized at altitudes of 90 to, let's say, 110 kilometer altitude. But it also creates a trail of ionized particles made of electrons and ions. Why? Because these tiny particles, they enter the atmosphere at really high speeds, called hypersonic velocities. It's at least something like 40,000 kilometers per hour. It can be much more than that, actually. So because of this speed, they have enough energy to, let's say, take electrons from the molecules and atoms that these tiny particles impacts in the upper atmosphere. And also the vaporized particles from the object itself can also be impacted. And therefore this creates, along the path of the meteoroid, a trail of electrons and ions that is exemplified here. You have here the object itself, a shock wave in front, and then a trail of electrons and ions that creates along the meteoroid path. This trail, this is, in this case, this is the electrons that are important for reflection of radio wave. And the general principle is illustrated in this sketch. On the right here, you have a transmitter emitting at a certain frequency. And here on the left, you have a receiver tuned to the frequency of the transmitter. In this example, because of the large distance between the receiver and the transmitter, and because of the curvature of the Earth, the receiver cannot detect the direct signal. By direct signal, I mean the signal propagating on the ground, as it's illustrated here by this gray line. And the receiver cannot record anything because the transmitter appears below the horizon as seen from the receiver. So the receiver here can only record local noise, let's say, at this frequency. But we are interested, of course, for detection of reflection of radio waves by meteors. We want to send this wave mostly towards the sky. And here you have an example with this red line here, corresponding to some radio waves sent towards the sky. It goes unaffected through the atmosphere because we can explain that in a future video. We select a frequency so that it goes through the atmosphere without being unaffected or without being reflected. Unless a meteoroid enters the atmosphere and creates this trail of electrons that I just mentioned. This is the yellow arrow that you can see here. And in this case, under some circumstances, the radio wave can be reflected towards the ground, and under some geometrical conditions that I will explain in the next video, you can record a signal here at the receiver. And this signal is called, in the jargon that we use, a meteor echo. We call this technique a forward scatter because the transmitter and the receiver are not at the same location. When they are at the same location, we are talking about a more traditional meteor radar. There are two advantages of radio observations over optical observations. The first one, with optical observations, whether you use your eye or sensitive video cameras, you are limited by the fact that you have to observe at night, of course. And second, you need clear skies, so without any clouds, because the meteor phenomenon, the visual phenomenon, occurs at altitudes of 90 to 100 kilometers altitude, typically, so well above the clouds. So because of this, you have a limited time of observations with optical observations that you don't have with radio observations, because radio observation, you can send a wave during the day. Meteoroids fall into the atmosphere also during the day, and they will also create ionization that can reflect your radio wave. So you can do these observations 24 hours a day. Also, clouds, they don't affect the radio wave either. So so you can really do these observations 24 hours a day. And the second advantage is that we are sensitive to lower masses, because in the first two videos, I explained that most of the particles are really tiny particles entering the atmosphere, and they do not produce enough light to be detected from the ground with video cameras. But they always create a trail of electrons that can reflect the radio wave. So because of that, we can detect many more particles, the smaller ones, which are much more numerous. And so we are sensitive to detect more particles and therefore lower masses, lower size or lower masses. Roughly speaking, the duration of the meteor echo here depends, of course, on the lifetime of the trail of electrons created by the meteoroid. And roughly speaking, it depends on the size of the object. The larger the object, the more electrons it will create in the trail, and the longer it will take for this trail to disappear into the atmosphere. The electrons tend to scatter into the neutral ambient atmosphere. And so most of the meteor echoes produced by these really small particles that you cannot detect with optical observations, they last only a fraction of a second. And for those who are already used to the radio meteors terms that we use there in the forum, for example, this corresponds to the underdense meteor echoes, but we will come back to that later in other videos. So in the next video, I will explain you some geometrical consideration linked to this reflection of radio wave that explains why a given receiver cannot detect all meteor echoes, and why we had this idea of creating a network like the BRAMS network. Thank you for your attention.